Hello, I'm Nizhou Wu from TU Delft. Today I will be presenting our work Characterization, Modeling and Test of Synthetic and Ferromagnet Flip Defects in STT-MRAMs. This is a collaboration work with IMEC. We discovered this defect based on silicon measurement, so it has never been discussed in the prior art. STT-MRAM is an emerging memory technology. In recent years, it is gradually entering into commercialization stage. There are a lot of startups all over the world, in the US, in China, in Europe. Spin, for example, is a pioneer in this race, and pretty much all foundries are also in this race to push this technology to the market. And just like all semiconductor products, we need high quality test solutions, and they have to be cheaper and efficient. However, STT-MRAM has new failure mechanisms, and some of them are not well understood yet. Here you see a team image of 3 STT-MRAM cells. The bottom part and upper part are no different to a conventional CMOS process. However, the middle one is STT-MRAM device, which requires unique and new processing steps. It is like a plug-in component between two adjacent metal layers. And not all defects, especially those in the device, can be modeled with linear resistors, for example, pinhole defects. In this work, we identify new defects, and we demonstrate the conventional test approach fails to detect such a defect. Therefore, we apply device-aware test, and we propose magnetic march test to guarantee the detection of this defect. Next, I will introduce a little bit about STT-MRAM basics. Then I will show you how we discover new defects. We apply the conventional test approach to these defects and develop a march test. And then you will see this march test fails to detect the defects. As an alternative, we apply device-aware test. Actually, both test approaches consist of these 3 steps: defect modeling, fault modeling, and test solution generation. Actually, our DAT approach innovates in all these 3 steps. In the end, I will draw some conclusions. STT-MRAM device is called magnetic tunnel junction. It basically consists of 3 layers: tunnel barrier, reference layer, and hard layer. It has 2 states, parallel and anti-parallel, representing logic 0 and 1. To strongly pin the magnetization in the reference layer, a synthetic anti-ferromagnet is widely used in industry. So basically, it means these 2 layers are always anti-ferromagnetically coupled, so that the magnetizations in these 2 layers are always pointing to the opposite direction. But these 2 layers are both composed of some ferromagnetic materials, so they both generate 3 fields at the free layer, and this 3 field has a large impact on the device performance. There are a lot of technology parameters for the device, for example, TMR and the 3 field as I show here. STT-MRAM cell consists of MTJ device and an NMOS as the selector. There are basically 3 operations: write 0, write 1, and read operation. So there are 3 key electrical parameters for the device: the resistance of the device, critical switching current, and the switching time. So apart from electrical current, you can also apply a magnetic field to switch the MTJ states. So if there is a defect in MTJ device, and these defects may impact the technology parameters, and in turn, electrical parameters will be impacted as a result. When we got a new lot of wafer, it is a routine to do some magnetic characterization. We found something very strange. The majority of STT-MRAM cells show RH loop at the top, but a small fraction of cells show an RH loop at the bottom, which is horizontally flipped. And you can also notice that these 2 loops are not symmetric at the vertical line where the field is 0. The top one shifts to the right side, while the bottom one shifts to the left side. and this indicates there is a 3 fields at the failure, and the polarity in these two cases are different. We also did electrical characterization, and you can see there is no difference in the shape of RH loop. We name this defect as synthetic anti-ferromagnet flip defects. And how do we know that this abnormal phenomenon is caused by this defect? Well, because this RH loop flips horizontally, the only reason is that the reference layer flips to the opposite direction. And because the reference layer and hard layer are anti-ferromagnetically coupled, so the hard layer must flip as well. Therefore, we call this SAFF flip, in short, SAFF. And in this situation, because these two layers both flip, so the 3 fields from these two layers at the failure also flip to the opposite direction compared to the good device. This is also consistent with our measurement data because the 3 field is equal to the offset field, but the polarity is reversed, and this one shift to the left side and the top one shift to the right side. Now we can do defect modeling. Using a conventional approach, we can just add a resistive bridge in parallel with a defect-free MTJ. We can also add a resistive open in series with the defect-free MTJ. In both cases, we actually neglect the physical defect mechanism. Next, we do fault modeling. We simulate a 3x3 memory array, and we assume the central cell has a SAFF defect. Then we just inject a resistor into this cell. We assume all neighboring cells are defect-free. Then we generated all necessary stimuli. We sweep the resistance value, and we perform circuit simulations and fault analysis. If there is a fault primitive compared to the simulation results without any defects, then we note down this fault primitive and move on to the next iteration. We use fault primitive notation to describe memory faults. It has 3 parts. The first part is sensitizing sequence. For example, a RAID 0 can be denoted as 0, RAID 0. The second part is faulty effects. For example, a RAID 0 operation make a cell flip from 0 to 1. The third part is readout value. For example, we intend to read out 0, but we end up with the wrong value 1. If we combine these 3 parts, we get a complete fault primitive. Now let's take a look at the fault modeling results. By using the conventional approach, we got 4 fault primitives. There are 2 transition faults and 2 incorrect rate faults. Next, we can do test generation. Each fault primitive has its own detection condition. For example, the first transition fault, we have to first initialize the cell to 0, then apply an up transition right, then read back the value. If we get 0 instead of 1, then we can see this fault primitive is detected. By merging these 4 fault detection conditions, we can get a March test. Now the question is, can we really use this March test to detect the SAFF defect? Well, we found the answer is no. We applied this March test to a large STT-MRAM array. For a defect-free cell, we can see the state starts with 0, then after write 1 operation, it goes to state 1, then it goes back to state 0 with write 0 operation. So these 2 rate operations both return the correct values. In contrast, for a defective cell, the loop shape is exactly the same. This shows that these 2 rate operations also give us the correct values. Therefore, the conventional test approach fails to detect the SAFF defects. Next, we apply device-level tests to the SAFF defects. The first step of DAT is defect modeling. The defect modeling process requires 2 inputs. First, a defect-free MTJ model. Second, a SAFF defective MTJ. In the end, we would like to get an optimized defective MTJ model which accurately captures a defect behavior. The first step we do is physical defect modeling. We categorize the physical defect based on silicon measurements. Then we identify the technology parameters that are influenced by the defects. And then we incorporate the effects of the physical defect into the technology parameters. The second step is electrical modeling of the defective device, which means we map the effective technology parameters into the electrical parameters. The third step we can do is fitting and model optimization. We can fit the defective device model to the measured silicon data, and by iterating this process, we can keep improving our device model, and this allows us to get an optimized defective MTJ model, which bridges the physical and the electrical levels. This slide shows some defect modeling results. In the defect characterization part, we have learned that the strip field at the free layer is the only technology parameter that is influenced by the defects. Therefore, we have to physically model this technology parameter in the presence of defects. So the strip field has two components. First, the strip field can be from the cell itself, from the reference layer and hard layer. And second, all neighboring cells also generate strip fields acting on the victim cell. We build up a 3x3 memory array. We assume the central cell is defective and all neighboring cells are defect-free. And on the right side, you can see how the strip field changes with the array pitch, the MTJ size. Here I use ECD, which means the electrical diameter of the MTJ device. And also the strip field also depends on the date pattern in the neighborhood. These three parameters have a large impact on the overall strip field. And once we get a physical model for the strip field, we can map it to electrical parameters of MTJ. And we know that the device resistance is not impacted by the SAFF defects. However, the critical switching current and the switching time is influenced by the defects. We use the physical model from this paper. Then we map it, the strip field to these two electrical parameters. For the details of the modeling process, please refer to my paper. And third, we can do fitting and model optimization. So on the right side, you can see our simulation curves matches the measurement data very well, and this shows that we can test our MTJ model, then use this defective MTJ model for fault modeling. Then we do device-aware fault modeling. Again, we simulated a 3x3 STT-MRAM array, and we assume the central cell is defective with the SAFF defects. The simulation procedure is the same as the conventional approach. The only difference is that in our DAT approach, we replace the defect-free MTJ model with our defective MTJ model. However, in the conventional approach, we just injected a linear resistor as a defect model. The fault modeling result is shown in this table. DAT gives us a unique fault primitive. It is intermittent, passive neighborhood pattern sensitive fault. This fault means that when all neighboring cells are in state 1, and if you apply a down transition operation on a victim cell, this operation fails intermittently with a certain probability. We can also compare the fault modeling results between these two different approaches. So the DAT approach leads to a intermittent fault, while the conventional approach gives us 4 fault primitives. And you can see there is no overlap between these two different approaches. And this shows that for the SAFF defects, the conventional approach leads to wrong sensitive fault primitives. But maybe these 4 fault primitives can represent other defects or partially represent other defects. And in contrast, our DAT approach gives us a unique and a realistic fault primitive. This fault primitive can accurately represent the faulty behavior of the SAFF defects. Finally, we do device-aware test. Based on this fault primitive, we can get a detection condition. To detect this fault, we have to set a date background at all ones, then apply a down transition operation. Based on this, we can get a functional merge test. Because the fault is intermittent, then we have to repeat the second part a number of times to increase the detection probability. For example, if you repeat 19 times, you can probably detect this fault. But of course, this test is very expensive. We also provide a better test solution, which is magnetic merge test. Conventionally, when people talk about merge test, they mean electrical operations. But here, we are the first one to propose magnetic merge test, which incorporates magnetic write operations. So for example, you can use this magnetic merge test to guarantee the detection of the SAFF defects. How does this work? I will show you. So we have a defect-free MTJ, and we also have a SAFF-defective MTJ. And we can apply a magnetic write to zero operation, and no matter what stays in your MTJ device, the magnetization direction in the free layer always align with the external magnetic field, and the same for the defective MTJ. And if you pay more attention to these two devices, you will see the defect-free MTJ is now in P state, while the defective MTJ is now in AP state. Then we can simply apply a rate operation to detect these SAFF defects. Compared to the first test solution, magnetic merge test is more efficient and cheaper, and more importantly, you can 100% guarantee the detection. To save your test time, you can also apply a magnetic write operation to an entire die or even entire wafer. But of course, you have to incorporate magnetic tools to generate magnetic field in your test facilities. Okay, let me conclude my presentation. STT-MRAM has unique failure mechanism. Some of them have not been well understood yet. For example, in this work, we present SAFF defect in MTJ device. We also propose test solutions to detect these defects. We demonstrate that the conventional test approach is deficient for STT-MRAM. This is because linear resistors are not qualified to model all defects. It may sensitize unrealistic faults, leading to waste of your test time and test escape. It results in low quality and inefficient test solution. As an alternative, we also demonstrate DAT is better than the conventional test approach. This is because DAT gives us more accurate and realistic fault models. It leads to optimal, efficient test solution. DAT is also very useful for fast diagnosis and year learning. This is because now each defect has unique fault signature. DAT is also applicable to other memories as well as logic circuits. Okay, that's all I've got. Thank you for your attention.